system, the distribution of the different components in different phases without much complication. Otherwise, for example, if you have a reactive system, you add component 1 with component 2, you will have 1, 2 and the same one as well. So how the same one will behave has to be encountered, right? So in this case, can you see? One of the component is what? One of the variables is temperature of the system. Second, and then third one is a concentration of each and every component in all the phases. Which means if I have phase 1 and phase 2, you have to know the component that is present in both the phases. In our case, we are looking at a non-reactive system. So 2 phases will basically mean that phase 1 will be one component, phase 2 will be another component. Okay? For each phase, we will have to specify the values of C concentration, and thus the P phases will have to be, so we go like this, the number of phases and the component that is present in that phase. Clear? The total number of variables here is PC plus 2. So that 2 that I am getting in the formula is due to the temperature and if I say that the system was done and was at constant pressure, then this formula here will become PC plus 1 because pressure has been removed. Right? If it's the single was done in the isothermal condition, then temperature is gone. So you will have PC plus 1. If isobaric and isothermal, that means you have fixed the temperature and the pressure, then these two gone. F is equals to PC. So basically, if you look at it, total number of equations that I just explained to you is just written in mathematical form. So that's how you are basically able to get C minus P plus 2. Okay? Any difficulty in the phase rule? Understood now? The only problem you will face is when the question will be given and you can't identify how many components are there, how many phases are there. That will be the problem. And in reality, what do? We just don't take water. Doctors don't advise you to take water when you are sick. What do you have to take? We have to buy Powerade. What is inside Powerade? Not nutrient. It has got ion, which I will explain in electrochemistry when we talk about the ionic strength of the liquid. So the ionic strength of the liquid should match that of your blood. If you only take water, then it gets diluted. That's why when you go to the hospital, the drink doesn't contain water, it contains salt. So when it goes in and it's usually injected again because you have balanced your the isotonic system in your body is that your ions are now whatever concentration is required is there. Now moving on to the phase diagram. So this is basically what you did in the lab. You started somewhere here, right? So what did we do? The whole graph went down. So then we went up this way. So what we are trying to look at in this case is that this is the atmospheric pressure, this is 100. From this part here, we started from somewhere here, and we went all the way up to this point here. So the portion of of the graph is basically somewhere here. Right? If we have done the lab, then you recall. Those of you who are asking for growth credit in the lab, please revolve the lab as well. It doesn't mean you just get the mark, then you forget the lab. Okay? So, what we did in the lab was basically decrease the pressure and then started looking at the boiling point. As soon as we came to atmospheric pressure, where the H became 0, it means the pressure inside is equal to the atmospheric pressure. So you started somewhere around 80 and finished off at 100. And then in your lab report, you are supposed to draw a graph of pressure versus temperature. And then at this point here at 100 degrees, you are asked to calculate the tangent. So, when you get this data, you plot it against the pressure against temperature. Make sure it's scattered. Then you go and select line of best fit. Oh, sorry, not line of best fit. Equation of best fit. It should be polynomial second degree. That means it should be to the power 2. So the equation that you will get on the graph will be y is equals to x squared plus x plus c. Clear? If you want to get the tangent to this point here, what do? You differentiate that equation. Remember in high school, if you get a graph, you differentiate the equation, it gives you the tangent to that point. Okay? That's what you have to do in the lab. So draw that part of the graph first. On Excel, get the equation that best fits. So I'm telling you, it's going to be polynomial, second level. And then you need to differentiate that equation, and the place where you have the value of x, it should be 100 degrees. And that will give you the tangent to the graph. So, the tangent to this graph here is what? The tangent to the graph is what? It's not chemistry, it's your high school maths. When you differentiate a graph, what will you get a tangent? The tangent is what? Slope. So the slope of the graph here is change in t over change in t. You see the difficulty I am facing? I shouldn't be teaching you the math from high school. You should know there that when you are doing the graph, you get the equation. When you differentiate the equation, you get a tangent. The tangent is the slope to the graph. Yes or no? And that slope means change in y over change in x, which is change in y over change in x. In this case, the change in y is what? P. And this one here is t. That's why you get to dp over dt. Anyway, I've shown you this graph here. This is how the water will behave in different states or different phases. This is the critical point, and this is the triple point. At the triple point, all the three phases are existing together. Degree of freedom is. At the triple point, the degree of freedom is. Zero. That is the only condition where you can get this water in three phases. C minus P plus 2. C is 1, P is 3, plus 2, answer is 0. It is invariant. Here is the critical point. After that, it goes into now we derive that formula dP over dt. At equilibrium, the free energy in the liquid state is same as the free energy in the solid state. along the equilibrium line. That is why the two phases exist. Along this line, the two phases exist. Here it will be liquid solid. This one here is going to be liquid vapor. This is what? Solid melting point or boiling point? This one is a melting point or boiling point? Melting. Solid liquid is melting. Liquid gas is boiling. So this is the equilibrium boiling point. This is the equilibrium melting point. This part here will be known when we come across the Clapeyron equation. This part here will be the closest Clapeyron equation. At equilibrium, delta G is 0. Remember when I was explaining about spontaneous reaction, non-spontaneous reaction, equilibrium reaction? Spontaneous is delta G is negative. Non-spontaneous delta G is positive. Equilibrium delta G is 0. Now I want you to do one thing. dG is equal to VdP minus SdT. Right? dG is equal to, remember this one?
VdP minus SdT.
Here? dG is equal to VdP minus SdT. That's in the liquid state. The same equation will apply in the gas state, because the gas will have some free energy, the liquid will have some free energy. So write that equation again. To differentiate the two, maybe you might put L here, L here, L here, that's liquid. Then the same equation you might write gas, G for gas. Okay? Along this line, G solid or G liquid is equal to G solid. Along this line, G liquid is equal to G gas. Can I put G liquid is equal to G gas? Do that. That means the two equations now become equal. dG is equal to dG. This is equals to this, but one is in the liquid phase, one is in the gas phase. This means some part here will be in the liquid, this part here will be in the gas. Done? So you will get VdP liquid minus SdT liquid is equal to VdP gas minus SdT gas. Right? Can you factorize it now? Bring the P on one side, DP and DT on one side, S and V on one side. Can you do that part? Remember, you get VdP minus SdT is equal to VdP minus SdT. One will be for the liquid and one will be for the gas. Now you bring that dP and dt on one side, S and V on one side. So what do you do? See what I did? This is equal to this. I told you to put dP on one side, dP and dt on one side, V and S on one side. So in this case, you can take the V that side first and bring the S this side. So you get something like this. And then after that, you take the dt that side and bring this one this side. And then you end up with this. And finally you come up here. If you are finding to factorize these algebraic forms, then this is not chemistry, this is maths. So please, if your maths is a bit weak, you didn't understand, it doesn't mean you have to stop and say this pose is hard. You just have to go back and revise how to factorize. There's a lot of internet. Remember in the tutorial I was saying, when you plug this and start listening to the music, it's good you plug this and listen how to do calculus. So, to replace the delta S, we use the Gibbs equation and make delta S the subject of the formula. You come up with delta H over T, and that's how you get this variable here. And you must have seen that in your lab, you are dealing with the Clipperton equation. This is how it came. This Clipperton equation is used for the melting equilibrium, solid to liquid. For the vaporization of, that is from boiling liquid to gas, we need to make one assumption. The gas behaves like an ideal gas. So, PV is equal to nRT. Remember, this equation is going to be used here, along this line here. Along this line, we have the liquid and the gas. And when it goes into the gas phase, the gas will start behaving like an ideal gas. Which means the gas will follow PV is equal to nRT. You must have seen in the lab, the flask that contained the water was very small. But there was a 5-liter big flask in which we did not want the water droplet to come in. So which means that a very small amount of liquid, water when it started to boil, it occupied a large volume so that the gas behaved like an ideal gas. Right? So, PV is equal to nRT. Then V that we have there can be assumed to be the volume of the final gas. Why? During boiling, there is a change of volume of the liquid to the gas. That means a drop of water in the liquid form has to occupy a large volume in the gas form so that it becomes an ideal gas condition. So a very large volume minus a small volume, the change in V is same as the volume of the gas. It's like this, 1 ml occupying 100, right? So 100 minus 1 is 99. So the change in volume in this formula, right? This change in volume in the formula is same as volume of gas minus volume of liquid. So one drop, 1 ml going into 100 ml, B, change in volume is 99, which is close to which one? The volume of the gas. Clear? So if I use the ideal gas equation, PV is equal to nRT, and if the change in volume is same as the volume of the gas, can I replace that part here? Do it. Make B the subject of the formula and plug in where delta V is. PV is equal to nRT, V is equal to nRT over P. Plug that part there. What do you get? PV is equal to nRT, make V the subject of the formula. And if you are dealing with one model, then N goes there. So basically this is what you get. The place where you have the dB is now replaced by the ideal gas equation here. And this is what I explained. The volume of the gas is so large compared to the volume of the liquid that is to be boiled, the change in V is equal to the volume of the gas. That one is used in for the equilibrium of solid to liquid. This one here is for liquid to gas. Can you see something here? dP over dt. If you go back to this equation here, you see when you are trying to derive this equation, dP over dt is same as ds over dv. dv. That is change in S and change in dv, ds, right? D means differential, triangle means differential as well. If I do this, I get the slope, that value is also equivalent to change in S over change in V. See that? The relationship. If it's dt over dp, then this will become, if this is dt over dp, then this will become dv over ds. Just change the graph, isn't it? You know how I catch the students? I gave a question. The graph was not P versus TA. The graph which is Y is P and X is T. So your slope is dP over dt, which is equivalent to that, which then comes here. I wanted to check if people, when they come to my class, when they go to sleep, then I can wake them up in the test. How? I changed the graph. The y-axis became t and the x-axis became p. The slope was dt over dp. So what the student had to do was calculate the slope and inverse to make it dp over dt. And that year no one asked a question. That shows that they came to my class, so they basically try to copy whatever is here and click. The idea for me to come here and not to give you this and say this is what's coming. You are supposed to go and read between the lines, so that you are able to know what this means. Change in y over change in x. It means the graph is y and x. Yes or no? In this case, it means the y is p, x is t. So dp over dt, I can make it dt over dp, isn't it? So you need to know the relationship, what it means and why we are drawing that graph. Where will I get that value from the experiment? Where will I get this value, dp over dt, from your experiment that you have done? Remember, from the graph, you will plot p versus t. You will get the equation of the graph. Then you will differentiate the graph, so that it becomes a linear equation. Then the slope of the linear equation is equal to dp over dt. Clear? That's all I have for you today. I think I've done too much for you, and all I can see the faces have changed.